Hello everyone. In this video, we are going to talk about PWM or pulse width modulation that you probably have heard or some of you may have used in order to control the speed of a DC motor. So here we're going to look a little bit deeper into that, and I'm going to show you, as you can see here, an example of a DC motor, the speed of which is controlled by PWM. So the PWM is coming from Arduino, and the duty cycle of that is controlled by this pot here. The transistor is there, which I explained, and this is my DC motor. Okay, now I have attached this kind of tape to it, and it is spinning relatively fast. Maybe you can hear it better if I bump up. Okay, so now it is going very fast, and then I can slow down until it almost stops. Like here at small duty cycles, the friction is more than the juice from the motor to the torque from the motor to turn it. So if I go up a little bit, it starts to spin a little bit faster, right? And then you see now it can go back, and I can speed it up, and I can go very high. Right, this is the maximum it can spin right now, and I can go down again. So here is the example that I'm doing, and if I go back here, my code, you can see it's very simple. Basically, I'm controlling the PWM through PWM pin 3. And then the pot is reading the duty cycle through pin A0 analog read. So that's all it is. So here, and you see I'm showing the duty cycle over there. So that is the essence of PWM. This is the circuit for it that I got from this website. That's a very good website. Explained that very well. So this is my Arduino again. You see pin 3 is going through the base of the transistor. Also base is connected to the ground with this 1K resistor. Then the collector is connected to the negative side, and positive side of the motor through this 20 ohm is connected to the power supply. And power supply here, you can see my power supply, right? That's this guy here. And we're going to talk about it, that you don't want to power your motor ever through the Arduino and fry the Arduino, okay? And then here is the negative side of the battery that is going through the emitter of this transistor here, okay? And then you have the pod, of course, that one side of it is connected to ground, the other is connected to high volt 5, and the other is going to A0 to read the duty cycle. So this is the entire circuit that I have. But here I showed you how this one is working and how I can turn the pot, right, to change the speed of it, and you can hear it again. Right, you can hear it. I had to tape it down, the motor. It was moving too much and making too much noise. So I taped it down and put something underneath it so the metal terminals do not make noise with the surface that is under it. So you see here, right, it is going all the way down, and you see now it is almost completely stationary, although the duty cycle here is about 10-15%. But the friction in the system is high enough that a 10-15% duty cycle is not even capable of rotating this small electric tape that I put on it. Forget about a real load. So I stopped the motor so it doesn't make too much noise. And let's go back to the screen so I can explain a little bit more about the theory behind PWM. And we're going to solve a problem with numerical values. So you see that although PWM looks very, very simple on the surface, if you want to choose the appropriate values and resistors and everything and motor and so on, if you want to finalize the decision for how fast you want to go for a specific torque, what duty cycle you need, you need to do some calculations at the end, okay? If you don't want to have some basically sensor that senses the RPM and senses the torque on the paper, if you want to pick a duty cycle, you have to do some calculations, okay? So we're going to talk about that. And before I go to that, I want to explain a little bit what is going on here in this circuit, okay? Two components I want to focus on. One is why do we have a separate power supply here? You see here I'm providing a 9 volt through my power supply. Why don't I directly get it from the Arduino? The second one is why do I need to connect here the base of this transistor to the ground? Because the base of it is controlled by pin D3. It's also connected by a resistor to the ground, by a pull down resistor. Why do we need that? So I'm going to explain those before we jump into the theory of PWM. So here I turned everything down so it doesn't make noise while I go through the rest of the material. So first thing is, as I said, you never ever want to directly power a DC motor, okay, or even servo or stepper really, but definitely DC motor. You don't want to power them directly through any pin of Arduino. So you might say, well, in this case, I go ahead and connect the negative of the motor to the ground, the positive of that directly to pin 3, and forget about this transistor and forget about that power supply. Well, the problem is the DC motor typically needs a lot more current than your Arduino can provide. You definitely do not want to pull anything more than 40 milliamp out of any pin of Arduino, and you want to keep it within 20 mils to be safe. So Arduino is really meant for logic control, okay, not juicing direct operations of electronics that need high current, because a DC motor can go milliamps to several amps. Depends on how much load you put on it, because you know the torque is proportional to the current. So if you apply too much load on it, that means a lot of torque, a lot of current, and a lot of current means you're going to fry the pins of Arduino. So you don't want to do that. You want to have its own power supply for the DC motor, and you want to just control the speed of the DC motor through the PWM. So what you do is you directly connect the motor to the 9 volt here, okay? And you even have some resistor here to limit the current going through the terminal of DC motor. Now, in order to control the behavior of the DC motor and be able to turn it on and off through PWM, you are using a transistor here, okay? And I'll explain the transistor, and then I explain this extra pull-down resistor here. Okay, so remember, the Arduino should not directly power the DC motor, because most of the time it does not even have enough current to make it rotate, and you're going to get it damaged. You're going to get the pins damaged. Now, why do you connect the transistor? Okay, why do you use the transistor, and why do you connect the base of the transistor by a pull down resistor to the ground? So let's talk about that one. So the first thing is, the transistor, as I said, is used to control the PWM, right? Because basically it acts as a switch. So when you send the voltage on and off at a very high frequency to the DC motor, this is the voltage coming through pin 3, you do on and off, and this is basically a switching behavior. To make that switching behavior happen, you need a transistor, and this transistor is TIP29. This is an NPN transistor. And the pins are, as you can see, 1 is the base, 2 is the collector, 3 is the emitter, when you can see that. So I have this pin here. And now let's talk about the pull down resistor here, which is a 1K ohm in this case. Why do you need that? The first one is to ensure that the transistor fully turns off. When I want it to fully turn off right here, okay, so what I would send through pin 3 is a low voltage. I send a low voltage and I expect the transistor to shut down the circuit. But even a small amount of leakage current through the transistor can keep it on, okay? But when you connect that collector pin that's the base pin. Sorry, when you connect the base pin here, base is the switch pin. Remember, base is the one that receives the low or high and decides whether it should connect or disconnect. So when you connect that to the ground, if you trace it down, you see it goes to the ground. This pull down resistor here will make that leakage current go away and it actually be 0 volt or low volt. So it properly turns off by connecting it to the ground. So the motor does not do any unwanted, unpredicted behavior. The other one similar to that is preventing floating inputs. So if your Arduino is not exactly in a high or a low, like first when you start it, then the base of the transistor will not necessarily be on or off. It might be in a floated stage, but when you connect it to the ground, it will be off, okay? And you're not going to see anything unpredicted. And also it makes the PWM switching to be faster. Okay, when your PWM of Arduino goes from high to low or low to high, the base charge needs to go away very quickly, because if the base has some voltage, some charge behind it, it is going to stay on, and if it doesn't, it goes off. But when it switches, that current, that voltage, the charge that was on it now has to go very fast to 0, so it goes from high voltage to the low voltage. And this grounding it through the pull down resistor will make that current go away very fast. So now you can basically do the switching better. So you want to have this pull down resistor directly connected to the ground for the base. So when you go from on to off, it actually goes off and it actually goes to 0 volt. So you need this extra branch here, not just this one. Okay. And clearly you see that the collector here, pin 2, is taking the juice out of this, and the 9 volt is bringing the voltage in. Good. So your pot is directly sending the value to pin A0. Now, of course, you know that when you do a pot, the value that pin A0 is reading through analog read, that number is a 10-digit, 10-bit representation, so it is between 0 to 1024, but the value you want to send out to the PWM pin is between 0 to 255. So you have to use the map function and convert that number, which is between 0 to 1023 to 0 to 255. Now you can use pin 3 with this duty cycle and use analog write, which is actually a PWM, and send it out. And here you can show it on the screen as I just showed for you. Okay. And here I'm dividing it by 255 to convert it to percentage, because I want to show it as from 0 to 100, not 0 to 255. So I divided by 255 to convert it to a percentage, as you can see here. Okay, so this is about the circuit and explaining the circuit. Now, going back to the theory of PWM. So is that the only way to change the speed of a DC motor? The answer is no. As you know, the speed of a DC motor, I had one of my previous videos, I explained to you that you can change it by a voltage, right? Let me show you brush DC motors. If we go back and look at this curve, I explained to you in this curve that the speed versus the torque is also a function of voltage. Remember, we had this relation here, the one in this red box. And you can see that if I have a fixed load, in this case just the inertia of that tape, then the speed depends really on the voltage. So if I can change the voltage applied to the DC motor, I'm allowed to move the omega up, right, or down if I reduce the omega. So why don't I use that? Okay, why don't I use the input voltage as opposed to turning it on and off at some variable frequency under my control? Well, the reason is it's not really super practical. Why not? Let's talk about this part. So there are several reasons that I mentioned for you here why you prefer this changing frequency of turning on and off and basically this duty cycle, the width of the part that is on, over changing directly the entire voltage. One is efficiency. Well, PWM is turning the motor voltage on and off rapidly, so it is reducing the total energy compared to having the voltage on all the time. So if I want to go from, let's say, 9 volt to 6 volt or 12 volt to 6 volt, one way is reduce the voltage through my power supply to that, but that power supply has to stay on all the time. But in here, instead of that, I'm gonna turn it on and off. So for a good portion of your cycle, you're not sending any voltage. So it's a little bit more efficient. The other one is how fast you can do that. Changing the voltage through this power supply needs me to go and turn these knobs on and off, right? That I can do, but if I want to do it automatically without this pot that I have here in the circuit, right? I can do that directly in Arduino by just changing the duty cycle. But here I have to wait on this guy to send me the voltage. So since it's done digitally and I can do it digitally as opposed to just manual, I can do it quickly and much faster. And then it is a little bit more precise and stable too, again, because that frequency is exactly under my control. That duty cycle is exactly under my control, as opposed to, again, something manual that you do. It's not as accurate. That exactly can go to the number I want here in the Arduino, but this one, I have to basically move it a lot back and forth to get it exactly to the number that I want. The other one is also torque maintenance. So when you're at lower speeds or higher torques, if you can reduce the voltage, it can cause a lot of loss of torque. Remember, voltage and torque and omega are related. So if you bring down the voltage, you lose a lot of torque. But here, PWM, because you don't change the maximum voltage, you keep the maximum voltage the same, you just change this width called the duty cycle, you can better keep the torque at lower omegas. And of course, because you're not using the voltage all the time, you're not generating as much heat and stress on the motor. So typically controlling the speed of the motor by PWM means your motor is going to live longer as opposed to directly controlling the voltage over that. So for several reasons, you want to use the PWM as opposed to changing the entire maximum voltage. So what is it that you exactly are doing? As I said, as opposed to sending this constant voltage, what you do is you switch this voltage on and off at a high frequency. So for some portion of it, you're going to get basically a periodic signal, right? You can see that this is a periodic signal and then it repeats and repeats and repeats. So during this period of the signal, which is basically 1 over that is the frequency of the PWM, during this one period, a portion of it, so much percentage of it, you keep the high voltage, which we call it duty cycle. So duty cycle is the on time over the entire period times 100%, and the rest of it, you keep it off. Now, because you are doing this switching at a very, very high frequency or very fast, the mechanical system cannot really catch up with that frequency. The time constant of the mechanical system for the DC motor, the shaft, is not basically that small that it can catch up with the frequency of the switching. So basically what the mechanical system will perceive is that your voltage has dropped from whatever it was to duty cycle times whatever it is now. So if duty cycle is 50%, now the voltage that you perceive, that's a keyword, in the mechanical system is like half of what it was in the beginning, okay, with 100% duty cycle. So this is the secret, is high frequency. That's the same thing that you kind of see when you look at movies, right? Movies are basically a bunch of frames, but you show them to the eye of the viewer at a high frequency, typically more than 18, 19, 20 frames per second, your eyes cannot see the transition from one to the next. You see it as continuous motion. That is kind of the same thing here. You do it very fast, okay? So the question is, what if the frequency of PWM is not high enough? Then what happens? Well, first is, what is a high frequency? Let's talk about that, and then we'll see what happens if it's not high enough. So the time constant for the mechanical part of the DC motor, permanent with permanent magnet brush DC motor, is typically a few milliseconds. So let's say 10 milliseconds. 10 milliseconds means 100 hertz. So the PWM frequency should be at least an order of magnitude above 100 hertz, which is somewhere like 1,000 hertz and above to like 20,000 hertz. So make sure that whatever the frequency of your system is, okay, then you go about 10 times at least bigger than that, so you don't see what we call start-stop response. So if the PWM frequency is not high enough, then what happens? Here you see that the voltage is high for a short duty cycle, and then it goes low and again high and again low, and it repeats. And then during the high period, the torque is going to go up, and then during the low, it has enough time, because the frequency of switching is not high enough. It has enough time to go down and then go up and go down and so on, okay? For that reason, you see these kind of ripples in the torque and in the current, of course, and the response that you get is called the start-stop response or jerky response. So to avoid that, you need to make sure that the frequency of your PWM is at least 10 times higher than the maximum frequency in your DC motor. Now, here I want to show you one example of calculating the required duty cycle for a specific task. So you learn about solving a mechatronics problem. So let's say we have a DC brush motor, and the type is an RS Pro 12 volt. It is controlled with PWM for the speed. Now, this motor has a rated voltage of 12 volts. The no load speed of that is 4,300 RPM or 450.77 radians per second. The no load current is 1.3 amps. The required speed that you need for your application is 3,000 RPM as opposed to 4,300. The stall torque of this motor is 0.1 Newton meter. The stall current is 5.5 amps. And the armature resistance, which you can say it's equal to the voltage divided by I of the stall, that is 2.18 ohms, okay? So here we divided that 12 by that 5.5, and of course that should be 2.18 ohms. Good. So now, as I said, you need to operate the motor at 3,000 RPM, and the torque you need to move the load is 0.04. So you see it's clearly below the stall torque. It's 40% of the stall torque, and this is the RPM that you need. You want to find what duty cycle do you need to achieve this task. So the first thing you do, you write here the Kirchhoff voltage law, right? So voltage of the supply, 12 volts, equals V of back EMF plus I of no load times R of the armature, okay? So this load can be written anytime, and here we are writing it for the no load condition. Now in the no load condition, we have the current 1.3 amps, and the resistance is 2.18. So the back EMF in that situation should be 9.166 volts, okay? Now you know that the back EMF is equal to the back EMF constant times omega. And in the no load condition, we have to use omega no load. So omega no load is also given to us, right? Look at it. That's this number here. So if, this one, this guy here. So if we divide that voltage by that omega, which is also at the no load, we can find the KE, and you know KT and KE, the torque constant and the back EMF constant, are the same value in the SI units. So in the SI units, if this guy is 0.0203, that is also KT. So what we found here was KE and KT of this motor. Of course, if we had the data sheet of that, we could have gone and read those numbers. But here, let's say we found them. Fine. Now, what is the torque that you need? The torque is equal to KT times I, okay? And the value you need is 0.04 Newton, and KT is we just found. So here you find the operating amperage, the operating current in the armature, right? So we found I, okay? Now the back EMF under operating condition is KE times omega under operating condition, and omega of the operating condition is this number. So you can find the back EMF under that condition is 6.38. Now the voltage drop across the resistance of the armature is I times R, and R is the value that we had up there, and I is what we just found. So this is the voltage drop across the resistance due to resistance. This is the voltage that you have to overcome, and that is the back EMF. If you add these two voltages, that's the total voltage you need to run the circuit. So the total voltage, if you add these numbers together, that's 10.67, but your maximum voltage is 12. So although you have 12 voltage that you run your system, practically what you need to run so much of current through the armature, because so much current comes from so much torque, and so much omega means so much back EMF, is 10.67. If you divide that by 12 by multiply by 100%, you see that the perceived voltage that you need is about 88-92% of Vmax. So that is your duty cycle. So the duty cycle that you need is about 88-89%. Now, of course, if this torque was smaller, then the voltage here drop would be smaller, because torque is smaller means current is smaller, current smaller means the voltage across resistance is smaller. So you get the smaller duty cycle. Or if the RPM was smaller, then the back EMF would have been smaller. Again, one of these would be smaller. So if you bring any of those two down, one of these two voltages go down, your duty cycle goes down. And you go up, your duty cycle goes up. Okay, so hopefully it is clear how we solve this mechatronics problem. And here I explain what is PWM, what is perceived voltage, what is the duty cycle, what is the frequency of PWM, why you would use PWM over directly controlling the voltage of a DC motor. And then I showed you this circuit aligned with the Arduino code that I'm gonna allow you to download it under video description. And also why we had to use this extra, basically pull down resistor, connect the base of the transistor to the ground, right? And why we need to use a transistor and an extra power supply, and we should never ever directly power the DC motor from Arduino, because we don't want to fry the Arduino pins. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.